Hello, I'm Gursimranjeet from NEC, and today I'll share the updates related to the NEC HPC offering named SX-Aurora TSUBASA. I'll start with the introduction of SX-Aurora vector engine. Then I'll share two use cases of SX-Aurora. One is for computational fluid dynamics, and the second is for combinatorial problems. Let me get started with the introduction first. SX-Aurora TSUBASA is the latest offering in NEC's SX series of vector computers. NEC has been making vector computers since 1980s. Through all these years, multiple vector computers from NEC have held the #1 spot in top 500 ranking. NEC is currently the only computer vendor in the industry that has continued to make pure vector supercomputers. Traditionally, NEC vector computers have only been deployed in supercomputer form factor. However, in 2018, NEC took a radical different approach and tried to democratize vector computer by making it available in different form factors. These form factors ranged from desktop tower to servers to supercomputer racks. This whole new product range is collectively named SX-Aurora TSUBASA. Each of these new products consists vector computer in the form of a PCIe card. This PCIe card is named Vector Engine. In 2018, NEC launched the first version of Vector Engine, and it was named VE10. VE10 was shortly followed with a minor update, which was named VE10E. At the SC20 event last year, we launched the latest vector engine, and this offering was named Vector Engine 20. Vector Engine 20 is available in two variants. One is Type 20A, which is water-cooled version of Vector Engine. The second is Type 20B, which is passively air-cooled version. The picture on the top right shows the layout of Vector Engine processor and the memory. On each Vector Engine PCIe card, vector processor as well as the HBM2 memory are located on the same silicon interposer. Also, Vector Engine has big fat processing cores that range between 8 to 10. All of this ensures a very high memory bandwidth between the vector processor cores and the HBM2 memory. The capacity of the HBM2 memory is 48 GB. Overall, Vector Engine is a very efficient processor, with most applications consuming power in the range of around 200 watt per card. Here, I'll just highlight the key performance characteristics of SX-Aurora TSUBASA. Tohoku University in Japan has recently completed a study where they compared SX-Aurora with various computer processors. They found that SX-Aurora has the highest bytes per flops ratio and also the highest overall efficiency when compared to other processors, including Fujitsu A64FX and NVIDIA V100. Hence, SX-Aurora seems best suited for those applications that, along with the computational performance, also demand very high memory performance as well. Now I'll talk about SX-Aurora TSUBASA for computational fluid dynamics. CFD simulations typically involve intensive computations that require large amounts of memory as well as the processing time for the quick and accurate results. We come in contact with laboratories for computational physics and fluid dynamics at the US Naval Research Labs. This department at the NRL explores and evaluates various emerging architectures for HPC applications. From our discussions with NRL, we discovered that even today, Many of the legacy CFD vector codes and their variations are still in use by Department of Defense. Achieving improved performance of these codes on new architecture is definitely expected, but without the time-consuming and labor-intensive refactoring of the existing millions of lines of code. So NRL went ahead with the legacy CFD solver, which is named FDL3DI. NRL aimed to accelerate this solver with SX-Aurora. This FDL3DI solver was originally developed in 1990s at the US Air Force Research Labs, and this code still retains its vector-friendly code structure. Typical applications of FDL3DI include wing vortex aerodynamics, flow control, and choke boundary layer intersection. Here, the results of NRL's FDL3DI evaluation has been shown. SX-Aurora vector engine is compared with various computing architectures. Uh, it is compared with dual-socket Intel Skylake and the Cascade Lake CPUs, as well as dual-socket AMD ROM CPU. As you can see, unsurprisingly, the bigger the dataset size, the better the vector engine performs. This comparison here is made between the optimized versions of FDL3DI on all the participating computer architectures. The original version of FDL3DI readily worked on SX Aurora without any code changes whatsoever. For the optimization part, NRL did the following changes. First, wherever possible, various nested loops were combined to vectorize those loops. And secondly, they used vector registers to store the performance critical arrays. This activity was done to eliminate the time-consuming dependency on x86 memory, where data had to be copied between memory and the accelerator all the time. So overall, this activity by NRL showcases that SX Aurora is extremely suitable for accelerating those CFD codes that operate on a big enough dataset size. Next, I'll talk about SX-Aurora TSUBASA for combinatorial problems. So multiple areas of computer science and application domains deal with the combinatorial problems. Finding the shortest or cheapest round trips or traveling salesman problems, planning, scheduling, supply chain optimization, circuit design, protein structure prediction are some of the examples of these combinatorial problems. However, the solution space of these problems is typically too large. So it's difficult to search for the optimal solution exhaustively using only the brute force method. So hence, annealing algorithms like simulated annealing and quantum annealing are used to accelerate the solution of these combinatorial problems. Talking about simulated annealing, it searches for the optimal solution probabilistically, whereas the quantum annealing searches the optimal solution using quantum effect. Simulated annealing is executed on digital or traditional computer processors, whereas quantum annealing is carried on with the quantum supercomputers that are in existence today. In the annealing algorithms, the combinatorial problem is represented by a quadratic, unconstrained binary optimization, or in simple words, as a cubo problem. So now to solve these combinatorial problems, NEC has developed a SX Aurora optimized simulated annealing engine. As shown in the bottom of the diagram, the simulated annealing engine is written in C++, and it has Python and C++ APIs for the purpose of user interface. In terms of the engine structure, it takes problems in the format of cubo. In terms of the problem size, one single vector engine card can take up to 100,000 qubits. Currently, the simulated annealing engine works with the single vector engine card only, but within next couple of months, we will be able to extend simulated annealing's capabilities so that it can support multiple vector engine cards. Because each vector engine can support up to 100,000 qubits, if a system encapsulates 8 vector engine cards, it will be able to work on the problem sizes up to 800,000 qubits. In terms of connectivity, the SA engine has 32-bit floating point based full connection. The simulated annealing engine has an extension which is based on external constraint. This extension is included to improve the results of the SA engine. I'll talk about this external constraint extension in an upcoming slide here. So the question would be, why anyone should use simulated annealing with SX-Aurora TSUBASA? And there are a couple of answers to this question. First, a simulated annealing algorithm is something which is very easily vectorizable. And being a vector processor, this suits SX-Aurora TSUBASA pretty well. Second, the kernel computation of this simulated annealing requires high memory bandwidth. And again, being a memory performance focused architecture, this is very much suitable to SX-Aurora TSUBASA. Also, the size of the problem is usually memory size constraint. As described earlier, the 48 gigabyte memory of vector engine PCI card can take up problem sizes of up to 100,000 qubits. So the large on-chip memory of the vector engine is very suitable to resolve these memory dependencies. When comparing NEC vector engine with the existing quantum computer solutions that are available currently, you will find that these quantum computing solutions, they are limited in terms of the number of qubits they support. So SX-Aurora can be very advantageous here, as it can be it can be complementary to these quantum computers as well as traditional CPUs to resolve very large combinatorial problems. And this hybrid of quantum computer and SX-Aurora can be readily realized. Recently, NEC and quantum computer maker D-Wave, we have partnered together to build hybrid tools of D-Wave's Leap Quantum Cloud Service. So NEC SX-Aurora can be readily integrated with D-Wave supercomputers, quantum computers, I would say. Lastly, I'll talk about the combinatorial clustering with NEC simulated annealing engine. So data clustering is a well-known method to analyze data for various data mining tasks, such as pattern recognition, image analysis, and machine learning. Combinatorial clustering is one form of the data clustering. It can be defined as the combinatorial problem. It can be defined as the combinatorial problem for the purpose of quantum and simulated annealing-based acceleration. However, the problem with the traditional combinatorial clustering is that when the data points increase, the quality of the combinatorial clustering degrades rapidly, not just on the traditional CPUs, but also on the quantum computers. There are a couple of reasons for this quality degradation. On the quantum computers, the reason is lack of high bit precision in the existing quantum computing solutions today. And in the case of CPUs, the issue is the inherent difficulty of working with large data points and large data in general. So with the partnership of the Hoku University, NEC has developed an extension of simulated annealing engine, which is named external constraint. We call it as SAEC. This extension of simulated annealing engine improves the clustering quality by several orders of magnitudes. In Tohoku University study, they found that compared to the conventional annealing methods, the speed up achieved by the simulated annealing engine is up to 256 times, which is a significant improvement. So this overall demonstrates that SX-Aurora TSUBASA is quite suitable for solving very large combinatorial problems. It can work independently, and it can work in a hybrid manner with the existing quantum computers and CPU solutions out there. So with this, I conclude my updates for today. I'll thank you for your time today.